Most users or programmers do not think of their programs as existing in one continuous linear address space. Rather, they tend to think of their memory in multiple segments, each dedicated to a particular use, such as code, data, the stack, the heap, etc. Memory segmentation supports this view by providing addresses with a segment number mapped to a segment base address and an offset from the beginning of that segment. For example, a C compiler might generate 5 segments for the user code, library code, global variables, the stack, and the heap, as shown in this figure. A segment table maps segment offset addresses to physical addresses, and simultaneously checks for invalid addresses, using a system similar to the page tables and relocation base registers discussed previously. This is an example of a segment table. Paging is a memory management scheme that allows processes' physical memory to be discontinuous, and which eliminates problems with fragmentation by allocating memory in equal-sized blocks known as pages. Paging eliminates most of the problems of the other methods discussed previously, and is the predominant memory management technique used today. The basic idea behind paging is to divide physical memory into a number of equal-sized blocks called frames, and to divide a program's logical memory space into blocks of the same size called NBSP, pages. Any page, from any process, can be placed into any available frame. The page table NBSP is used to look up what frame a particular page is stored in at the moment. In the following example, for instance, page 2 of the program's logical memory is currently stored in frame 3 of physical memory. A logical address consists of 2 parts: a page number in which the address resides, and an offset from the beginning of that page. The number of bits in the page number limits how many pages a single process can address. The number of bits in the offset determines the maximum size of each page, and should correspond to the system frame size. The page table maps the page number to a frame number, to yield a physical address which also has 2 parts: the frame number and the offset within that frame. The number of bits in the frame number determines how many frames the system can address, and the number of bits in the offset determines the size of each frame. Page numbers, frame numbers, and frame sizes are determined by the architecture, but are typically powers of 2, allowing addresses to be split at a certain number of bits. For example, if the logical address size is 2 to the power of m and the page size is 2 to the power of n, then the high-order mn bits of a logical address designate the page number and the remaining n bits represent the offset. Note also that the number of bits in the page number and the number of bits in the frame number do not have to be identical. The former determines the address range of the logical address space, and the latter relates to the physical address space. DOS used to use an addressing scheme with 16-bit frame numbers and 16-bit offsets, on hardware that only supported 24-bit hardware addresses. The result was a resolution of starting frame addresses finer than the size of a single frame, and multiple frame offset combinations that map to the same physical hardware address. Consider the following micro-example, in which a process has 16 bytes of logical memory, mapped in 4-byte pages into 32 bytes of physical memory. Presumably some other processes would be consuming the remaining 16 bytes of physical memory. Note that paging is like having a table of relocation registers, one for each page of the logical memory. There is no external fragmentation with paging. All blocks of physical memory are used, and there are no gaps in between and no problems with finding the right-sized hole for a particular chunk of memory. There is, however, internal fragmentation. Memory is allocated in chunks the size of a page, and on the average, the last page will only be half full, wasting on the average half a page of memory per process. Possibly more, if processes keep their code and data in separate pages. Larger page sizes waste more memory, but are more efficient in terms of overhead. Modern trends have been to increase page sizes, and some systems even have multiple size pages to try and make the best of both worlds. Page table entries are typically 32-bit numbers, allowing access to 2 to the power of 32 physical page frames. If those frames are 4 kilobytes in size each, that translates to 16 terabytes of addressable physical memory. When a process requests memory, for example when its code is loaded in from disk, free frames are allocated from a free frame list, and inserted into that process's page table. Processes are blocked from accessing anyone else's memory because all of their memory requests are mapped through their page table. There is no way for them to generate an address that maps into any other process's memory space. The operating system must keep track of each individual process's page table, updating it whenever the process's pages get moved in and out of memory, and applying the correct page table when processing system calls for a particular process. This all increases the overhead involved when swapping processes in and out of the CPU. The currently active page table must be updated to reflect the process that is currently running. Page lookups must be done for every memory reference, and whenever a process gets swapped in or out of the CPU, its page table must be swapped in and out too, along with the instruction registers. It is therefore appropriate to provide hardware support for this operation, in order to make it as fast as possible and to make process switches as fast as possible also. One option is to use a set of registers for the page table. For example, the DEC PDP-11 uses 16-bit addressing and 8 kilobytes pages, resulting in only 8 pages per process. It takes 13 bits to address 8 kilobytes of offset, leaving only 3 bits to define a page number. NBSP, an alternate option is to store the page table in main memory, and to use a single register, called the NBSP, Page Table Base Register or PTBR, to record where in memory the page table is located. Process switching is fast, because only the single register needs to be changed. However, memory access just got half as fast, because every memory access now requires 2 memory accesses. One to fetch the frame number from memory and then another one to access the desired memory location. The solution to this problem is to use a very special high-speed memory device called the Translation Look-Aside Buffer or TLB. The benefit of the TLB is that it can search an entire table for a key value in parallel, and if it is found anywhere in the table, then the corresponding lookup value is returned.